Okay, see Lindelof videos, AP Calculus. What I want to work on today is approximating the area under a curve, and I want to approximate this in an attempt to move towards Riemann sums. So we're going to use this sigma notation, and I'm going to introduce this in a second. But first thing I want to do is introduce this idea. So let's take this curve, and this might be a parabola that continues over here, or could be a thousand, could be a cubic that rolls out like this and then comes up. I don't know what it is, but I know that the only place I'm interested in this curve is between the x value a and the x value b. And what I want to know is, what's the approximate area under here? So I'm looking for this. This is what I'm looking for. I'm looking for this area here. Looking for this area. Wow. Wow, that's terrible. Right, I'm looking for this area here. I'm looking for all this area right here. Right, so I'm looking for this stuff here. All right, pretend that I got all that captured. So that's the area that I'm looking for. And the way I'm going to do that is this. I'm going to do this, it's called a right-hand sum. What I'm going to do is I'm going to just start breaking this thing out, and I'm going to say this. I'm going to say that I'm going to make these equal intervals here, and I'm going to use this left-hand sum. So what I'm going to do is this. I'm interested from A to B. So what I'm going to do is I'm going to say, I'm going to use this. I'm going to go over exactly this far. And then if you don't mind, I'm going to go over exactly that far again. Pretend that you believe that my artwork is really, really good and that these widths, these rectangles have the exact same base. And then I'm going to make another one. And you can see this is a left-hand sum because the corner of my rectangle touches, the left-hand corner of my rectangle touches the curve, right? And then I'm going to make the same size again. Oops. And then again, same thing. So this is my left-hand sum. So, and then pretend that, and that looks like crap, but if you don't mind, please pretend that all these bases look like they are exactly the same width. So what I'm going to do is I'm going to find all these areas. I'm going to find this area, plus this area, plus this area, plus this area, plus this area, and I'm going to add those together. I'm going to say the area under the curve that I'm interested in is approximately that amount. So let me give some detail to this. So I'm saying this. I'm going to approximate the area under a curve. And I'm going to say let f of x be non-negative on AB. And you can see that my curve is non-negative on AB. And we're going to find the area lying beneath the curve of f of x, so underneath the curve, but above the x-axis. So it has to be above the x-axis. This is something that will change, but for now we're just going to talk about above the x-axis. And we're going to say from x is equal to a to x is equal to b. So this is our first x value. This is our second one. So look at this for a second. I suggested to you that our bases were, my intention was to make them all the same width. So what I'm saying is that the width from here to here, this base right here, the base here is, I'm going to call that delta x or change of x. And if this is change of x, this base, then so is this one, and so is this one, and so is this one, and so is this one. They're all intended to be equal subintervals. Okay? So what I'm going to do with this, what I'm going to do is this. To figure out what this base is, I'm going to do this. I'm going to say that my base, delta x, change of x, this base of our rectangle, because the area of a rectangle is base times height, so I have to figure out what the base is going to be b minus a over the number of subintervals that I want. B minus a just gives me the distance between here and here, because I'm not suggesting to you that a must be 0. It could be 3 and this could be 8. So the distance, if this was 8 and this was 3, the distance would be 5, wouldn't it? So this is just the distance that we're going to travel, and this tells us how many equal pieces we want it broken into. So far, so good, I hope. So then I'm going to move on, and I'm going to start giving some name to this, because what I need is I need to figure out what this height is. So I'm going to say let the first x value be x sub 0. This is sub 0. And let the last x value be x sub n, last one in my interval. Yeah? Well, if that's true, then that makes this, if this is x sub 0, is this one, then the next one will be x sub 1, x sub 2, x sub 3. And if you don't mind, what I'm going to do here, instead of saying x sub 4, I'm going to say this. I'm going to say it's, if this is x sub n, then this is x sub n minus 1. Because I'm saying no matter how many intervals we have, and we can change the number of intervals, so I can use this method. And if you think about what we did to find that area, what we did was this, I think, right? We're going to say that the area, the approximate area, so the area is approximately equal to f of x sub 0, because that's the height. This is, remember, this is x sub 0 here, so this is f, the height of that, times change in x, isn't it? And then the height of the second rectangle when we're doing, this is a left-hand sum. This is left-hand sum. Hand-sum, that's funny. Left-hand sum, so the sum based on the rectangle, left-hand corner of the rectangle touching the curve. So this is our left-hand sum, so plus f of x sub 1 times change in x, right? This base, that's this one right here, this base right here is change of x. The height, right, we need base times height to get that. The height of it is this height right here, and that's the height at f of x sub 1, isn't it? This is f of x sub 1 right here is that height, isn't it? Plus all the other ones, all the way stopping to, but look, the last one, the last rectangle has a height of f of x minus n. So we have f of x sub n minus 1 here times change x. This is really important for a left-hand sum because we're not using this height here. We're using where it touches the curve here, right? So this is our left-hand sum. My point to you is this: as we go towards Riemann, we have to kind of move into this sigma notation. And sigma notation looks like this. It's the summation of a sub I as I goes from 1 to n. But we can give ours, in this case, real definition. We can really say what this is. And what we have, actually, is we have the summation of f of x sub I times change in x. But in this case, we know it's f of x sub 0 because it's a left-hand sum as I goes from 0 to n minus 1. 0 to n minus 1. And what this says is that all this says is this. This is the exact representation of this. All right? So I think this is okay. I'm going to go ahead and stop this video, and then I'm going to do a left-hand sum and talk about that because I don't want to overwhelm you with all this crap. But I do want to say to you that in this case, when we look at this, we can see clearly that this is an underestimate. This is a low estimate of what it is because we're missing all of these areas, right? We're not accruing these areas. We're not accounting for these areas, right? So we have the area that we come up with will be actually less than the exact value. Will be less than it. If you find, next thing we'll do is an overestimate, and then we'll be able to say for certain that the real area is between those two numbers. So hey, thanks for watching. This is really going to be important as we move towards Riemann sums. So again, thanks for watching. If you have any questions or comments, let me know. And if you haven't already subscribed, please subscribe. Thanks.